This conference will now be recorded.
Yes, good morning, students, and we'll start from where we left off in our last class. So last class, we were discussing about Beer-Lamberts law. We have seen what each of the two laws state, that is, what is Beer's law and what is Lamberts law. We have also seen how to derive an equation for the combined law, Beer and Lamberts law. So what Beer's law indicates is the absorbance of a solution is directly proportional to the concentration. Or in other words, whenever the concentration increases, the absorbance of the solution also increases. This is what Beer's law states. But this is true if the thickness or the path length is maintained constant. Now, what Lambert's law says is, for a given concentration, if the path length is changed, then the absorbance also changes. Or stating in another way, absorbance is directly proportional to the path length or the thickness of the absorbing medium, the length through which the radiation passes through the solution, that is the path length. Okay, so as the path length increases, the absorbance also increases. This is true for a single concentration, that is, the concentration is kept constant. So when these two laws are combined, we have a new law, that's Beer-Lamberts law, and that states that absorbance is directly proportional to both concentration as well as thickness, but not together. One should be maintained constant, then the other will be directly proportional to absorbance. So we also derive the equation A equals capital A equals small ABC, or we could take it as capital A equals epsilon BC, where epsilon is molar absorptivity, B is the path length in centimeters, and C is the concentration in moles per liter. This is Beer-Lamberts law. Now we'll go further from there, that is application of Beer's law to mixtures. Now, because when we say A equals epsilon BC, we are indicating that our sample solution has only one absorbing substance whose concentration is C, and absorbance of the solution would be directly proportional to the concentration of the absorbing substance. But what if your sample is a mixture of substances? That is, there are more than one substance in the sample solution, and all of them are capable of absorbing a given wavelength of radiation. In that case, we would have to make use of this formula, because when we measure the absorbance, you will get the total absorbance of the solution at that given wavelength. And that A total, what you get, would be the sum of absorbances of individual components in the sample. Now here I have given as A1 plus A2 plus A3 till AN, any number of components, where 1, 2, 3, these refer to the absorbing components. So suppose you have only 3 components, A1 plus A2 plus A3. And then you can actually expand each of this according to Beer-Lamberts law. A1 would be equal to epsilon 1 BC1, A2 equals epsilon 2 BC2, A3 equals epsilon 3 BC3. B is not given any subscript because it remains constant. Since it depends upon an instrumental component, the cuvette or the sample holder, which will have a definite diameter, and hence the distance from one end to the other end, or the solution contained, the length of the solution within that cuvette will be constant for all the substances. Epsilon 1 or epsilon is characteristic of a given substance, and hence we have the subscript epsilon 1 and epsilon 2 can be different. They will be different. It could be greater or lesser. And C1, C2, this is the concentration of a given substance in the sample mixture. C1 could be greater than C2, or it could be equal to C2, or it could be lesser than C2. So this is where I think we stopped last class. So this is, but this particular equation, A total equals A1 plus A2 plus A3 and so on, this is true only if there is no interactions between the individual components in the sample mixture. That is, one does not interact with two, or two does not interact with three. If that is true, then we can go ahead with this formula to calculate the concentrations of each one of these. Now we go further. We'll see what is a Beer's law plot, because for quantitative analysis by UV visible spectroscopy, we make use of the Beer's plot, which is the Beer's law plot. In short, we refer generally as Beer's plot. What is Beer's plot? It's a graph. So it's a plot of absorbance on the y-axis versus concentration on the x-axis. So this is what you see in this picture, absorbance on the y-axis versus concentration on the x-axis. Now, to construct a Beer's plot, you have to make a number of standard solutions of the given substance. What is a standard solution? A standard solution is one in which you know what is in the solution and how much of it is there in what volume. That means you know the content of the solution, and you also know what is the concentration of that substance in solution. So, say for example, you are preparing a number of standard solutions, standard 1, 2, 3, 4 as shown here. Standard 1 has got a given concentration, standard 2 has another concentration, 3 is a different concentration, 4 is a different concentration. Say standard 4 is 1 microgram per ml, 3 is 2 microgram per ml, 2 is 3 microgram per ml, and standard 1 is 4 microgram per ml. So the concentration is increasing as the numbers are decreasing. So this is the lowest concentration, then this, all are the same substance. So once you have prepared the standards of different concentration, you will measure the absorbance of each of these one by one at a given wavelength. Which wavelength? You will preferably choose the wavelength which equals the lambda max, or the absorption maximum for the given substance. So if the substance is, say, you have chosen something like paracetamol, you first find out the lambda max of paracetamol in the given solvent you are using for your experiment. How do you find lambda max? You will, if you remember from the previous class, it is lambda max is found by constructing a plot of absorbance versus the wavelength. That's the spectrum of paracetamol. So at different wavelengths, you measure the absorbance and then you draw the curve. Wherever you get the maximum absorbance, the wavelength corresponding to that is the lambda max. So once you choose your lambda max, you fix your lambda max at that given value, and then you measure the absorbance of each of these standard solutions of known concentration. Now you will get the absorbance of each of these solutions, plot it against its concentration. Say for example, this is the concentration of standard 4 and this is the absorbance. So you will put a dot here, you will mark this point. Next for standard 3, and this is the absorbance, so you put like this. Like this you will do for all the 4 standards, and then you draw a straight line passing through all these points and passing through the origin. This is a straight line plot passing through the origin, and it clearly indicates that because of the shape of the line, it clearly indicates as the concentration increases, the absorbance is also increasing. For a small concentration, the absorbance is this. For a larger concentration, the absorbance is higher. Still larger concentration, absorbance is still higher. So here it clearly shows absorbance is directly proportional to concentration, and that is what is stated by Beer's law. So here the Beer's plot indicates that absorbance is proportional to concentration. So this is a standard Beer's plot. Now from the standard Beer's plot, you can find out the concentration of any unknown solution having the same substance. So what you do is, you have been given a sample solution. You will take, say, 1 ml of the sample solution and dilute to 50 ml. So now whatever was given to you in 1 ml is present in 50 ml. So now what you do is, you will measure the absorbance. From the value of absorbance, you will draw a straight line till it intersects your graph, your standard plot. And from there, you will then draw a directly vertical line down. So this will end up in a given concentration. So this is the concentration of the unknown. Then you will put the dilution factor and find the exact concentration of your given sample solution. This is how we use Beer's law to find out the concentration of an unknown sample, by first constructing a Beer's plot and then finding the concentration. You can also do by another method, that is the slope method. What you do is, once you have constructed the standard plot, the red line, you can find the slope of this curve. That is, this is a straight line, so you can find the slope. How do you find the slope? You have to take 2 points, y2, y1, x2, x1. So this divided by this. I think you all know how to find the slope of a straight line curve. So here you will get, once you get the slope, then you can find, using that slope, you can find the concentration of any unknown sample given to you which contains the same substance. Because you have to prepare a solution of that substance in the same solvent, and then you can measure the absorbance. Absorbance divided by the slope will give you the concentration. Incorporate the dilution factor and get the exact concentration of the given sample solution. This is how you do it. You will be doing all this in your practicals. So you will become very thorough with this. So this is what we generally employ in our practicals to quantify given sample solutions. Now, like I told you, this is the ideal Beer's plot. That is a straight line passing through the origin, and also a straight line which shows absorbance is proportional to concentration. Because you could have a straight line like this, parallel to the x-axis. Okay, so that is not showing absorbance is proportional to concentration. So that's not an ideal Beer's law. Now, before we go into the other types of straight lines we could get, we will see about this, that is deviations which can be obtained. Now, if you see in this picture, in this plot, you see a straight line. This is the ideal Beer's law. You see a straight line passing through the origin and also indicating absorbance proportional to concentration. So this is the ideal plot. But sometimes what happens is, you will not get a straight line. You get a straight line to some extent, and then your plot, say, goes along the red line. So you have a turn like this. Or in some other cases, you may see a straight line to some extent, and then the curve starts bending towards the x-axis. That is, it follows the green line. If you get a green line plot, that indicates a negative deviation at certain concentration. If you get a red line plot, then it indicates a positive deviation at certain concentrations. So in this case, from this concentration to this concentration, you will say the Beer's law is being obeyed by the substance. But in the second graph, you see here, till you get this straight line. Till this, so the concentration directly corresponding to this. So from this to this concentration, the substance is obeying Beer's law. But at concentrations greater than this, the substance is showing deviation. That means it is not obeying Beer's law. So you should not use those concentrations when you are trying to quantify your sample solutions. You should stick to concentrations lower than this value. Suppose, say, your sample is highly concentrated, what you do is do multiple dilutions and get a concentration lower than this. That is, you should get an absorbance less than this value. So suppose your sample solution is giving a higher absorbance, it corresponds to a deviated portion of the standard plot, and hence you dilute the solution further until you get an absorbance for the sample which is lower than this. So then you can do the same what you have done in the left graph. You can draw a straight line to the standard Beer's plot, and from there you can take a directly vertical line downwards to the concentration axis and find the concentration. So these are some deviations which you see in Beer's plot when you change the concentration. Now, the other thing that I would like to tell at the, because here we need to discuss about variations in Beer's plot also. So regarding variations in Beer's plot, I will just draw you a graph here. Suppose this is your graph and you get a straight line in like this. Does it indicate that the substance is obeying Beer's law? What I have drawn here is, like here, see here what is happening is you are having a straight line, but I told you passing through the origin. Here it is not passing through the origin, but it is a straight line, clearly indicating as concentration is increased, absorbance is increasing. You could also have a graph like this. Consider this is also a straight line. So if you have a straight line like this straight line, not this one, okay. So here you have two graphs. Don't consider this one. Okay. Now you have so you consider this now. This straight line which indicates A is proportional to C. You also have this straight line which is A is proportional to C. In both the cases, we would say the substance is obeying Beer's law. But this is not the ideal Beer's plot. Why you have not got an ideal Beer's plot here? And can you get it? Yes, you can in most cases. Here what it signifies is at zero, because this is the concentration axis. So at zero concentration, you are getting some absorbance. Even when the sample is not there, some absorbance is being indicated. That means something else is absorbing other than your substance. So it could be something in solution. So it could be anything in solution. It could be the solvent, it could be impurities in solvent, various aspects, or some other reagents that you have added. So to avoid this sort of graph, what we generally do is we prepare a blank. A blank is a solution which has everything same as in the sample except the absorbing substance we are determining. Okay, suppose say we are determining paracetamol sample, then except paracetamol, All the other things in your sample solution should be present in the blank in the same concentration. Say you have dissolved paracetamol in zero point 0.1 normal HCl, then your blank will be zero point 0.1 normal HCl. If you have added some other reagent in your paracetamol solution, say 1 ml, then you will also have to add 1 ml in your blank solution. So that's a blank solution which has everything same as in the sample solution except the absorbing substance, or except the substance you want to determine. So if you use a blank solution and make the absorbance 0, then you will get exactly the same graph, but it will be lowered. It will come at this point. That is passing through the origin and parallel to the original graph. So this is not actually a deviation. This happens when a blank is not used to get 0 absorbance. To calibrate your instrument to show 0 absorbance with blank. Now coming to this one, does it indicate obeyance of Beer's law? Yes, again it indicates, because as concentration is increased, absorbance goes on increasing. You're increasing concentration, you're getting higher and higher absorbance. So A is proportional to C. That means the substance is obeying Beer's law. But it is not an ideal Beer's plot because it is crossing the x-axis at this point. It is not going through the origin. What this states is, below this particular concentration, substance will not obey Beer's law. But from this concentration and above this concentration till here, substance is obeying Beer's law. So whenever you're doing an analysis of this substance, use concentrations greater than this and less than this. So now when I'm putting a limit to the concentrations that can be used, that is nothing but Beer's law range for a given substance in a given solution. So you are sometimes asked a question, what is Beer's law range? So how do you determine Beer's law range? Beer's law range can be determined practically. How you do it is, you will make a series of standard solutions like this. Suppose you get a standard plot of this nature. What you have to do, this is your lowest concentration, so you make next set of standard solutions, starting with this as the highest concentration and go to lower concentrations. Okay, say this was 1, 2, 3. Now 1 will be your highest concentration in the second step. 1 is the higher and lower ones will be say 0.8, 0.6, 0.4, 0.2. Okay. Now again, if you get the same type of plot, then you know 0.2 it is obeying. So 0.2 will be your highest. So make smaller concentrations. That means you could make 0.15, 0.1, 0.5. Like this, go on stage by stage. You have to go to lower and lower concentrations till a time when you get a plot of this type. That means the straight line will not pass through the origin. Instead, it will intercept on the y-axis. The moment you get a concentration intercepting on the y-axis, you can consider that to be the lower limit of Beer's law range for your substance. So one limit you have found out, the lower limit. Now, because the range always, Beer's law range has a lower limit and an upper limit. So like this, we have found the lower limit. Similarly, say this is the highest concentration here. You're getting a straight line till the highest concentration. Say this is 5 microgram. So you make next set of solutions starting with 10, 20, 30, 40, 50. So if you still get a straight line, leave that. 50 is also giving straight line. Then you go to 100, 200, 300, 400, 500. Suppose you don't get a straight line, then you know 50 is giving, 100 is not giving. So in between, you make concentrations. That is 50, 60, 70, 80, 90. See till where you get a straight line. Suppose till 90 you are getting a straight line, 100 you're not getting, you're getting a deviation at 100, then 90 would be your upper limit. So like this, we can find out what is upper limit of Beer's law range. We can also find out what is lower limit of Beer's law range. This is found out by actually performing the experiment, and then we can say this is the Beer's law range. What is the importance? Whenever you are analyzing any samples, the sample concentration must lie within the Beer's law range. Only then absorbance will be proportional to the concentration. Otherwise, you end up with erroneous results. So now we come to another important topic, that is deviations from Beer's law. There are a number of deviations. Now, what constitutes a deviation, first of all? Because we know what is Beer's law. It states in simple terms that absorbance is proportional to concentration. So any deviation from direct proportionality between absorbance and concentration would constitute a deviation from Beer's law. Some also refer to it as limitations of Beer's law. They're the same whether you call it deviations or limitations. Okay, so deviations from Beer's law could be of three types. The first one is called real deviations, because these are fundamental deviations. You cannot eliminate these. You can only work within the limitations. Then you have second one, which is called chemical deviations, and the third one is the instrumental deviations. Instrumental deviations are again of two types. It could be due to polychromatic light being used, or it could be due to the presence of stray radiations. We'll see each one of these in detail. So we start off with real limitations. Now, these are some of the points that I have given under real deviations. Because this law is applicable only to dilute solutions. Beer's law is applicable only to dilute solutions. Now, what is dilute solution? That means in this case, the concentration should be less than 0.01 molar. So we cannot say it should be 1% solution or 2% solution. It varies based on the molecular weight of the given substance. So that's why the molarity is given. So concentration of a given solution should be less than 0.01 molar. Then it is considered an appropriate dilute solution. Now, what happens if the concentration is greater than 0.01 molar? That we should try and understand. So we'll know why the concentration should be less than 0.01 molar. So when you go for higher concentrations, the average distance between the particles in solution, because you're having the same container, okay, same volume of solution, but the concentration is greater. That means there are more number of molecules. So the average distance between particles is reduced now in a more concentrated solution. If the average distance becomes so less that each particle affects the charge distribution of its neighbors, then you will get a deviation. And this happens when you go to concentrations greater than 0.01 molar. So when the concentration exceeds 0.01 molar, the average distance between the particles reduces to an extent such that each particle affects the charge distribution of its neighbors. And when the charge distribution is affected, then the absorbance is also affected. So you don't get the correct absorbance as you would get in a dilute solution. You get an altered absorbance or an erroneous absorbance. That means you will get deviations from ideal Beer's plot. And therefore, to avoid this, and more the concentration, more this deviation, greater would be this deviation. And hence, we need to see that we use only dilute solutions if you want to prepare a Beer's plot, or you want to find the concentration of a sample using the standard Beer's plot. Now, sometimes what the situation could be is the sample solution has a concentration less than 0.01 molar, so there is no problem. But the sample solution has been prepared using other reagents, particularly electrolytes, and using these electrolytes in a high concentration. The sample concentration is low, but the concentration of other electrolytes is high. That means there are a lot of other ions other than your sample in solution. In this case also, you will get a deviation. This is because there will be a change in the molar absorptivity of your sample because of the presence of high concentration of these other ions. This happens because of electrostatic interactions. Because of the large number of other ions, there's a lot of electrostatic interactions which changes the molar absorptivity of your sample substance. And if you remember, Beer's law is A equals epsilon BC, and A is proportional to C. This is true if epsilon and B are constants. If epsilon changes, as in this case, then we don't know what is the proportionality constant between A and C. That also varies. It's not a constant anymore. So epsilon needs to be constant in order to get an ideal Beer's plot. Otherwise, there will be deviations. Another instance is, in some cases, when the concentration is increased, there's a lot of change in the solution. Maybe it becomes very viscous, but ultimately it may affect the refractive index of the solution. If refractive index gets altered by concentration changes, then also it will directly have an impact on the molar absorptivity. Molar absorptivity, if it changes with concentration, then there is a problem in Beer's law, because as I said, A equals epsilon BC, epsilon and B are supposed to be constants. If they are changing, then the proportionality between A and C is lost. But this is a very rare occurrence. This change in refractive index is very rarely seen because we are dealing with low concentrations. If you remember, less than 0.01 molar. At such low concentrations, it's very rare that you will see the refractive index will get changed. And if it doesn't change, there is no question of the molar absorptivity or epsilon changing. So this third thing is rarely seen, but the second one may be seen quite frequently. So what we should do is, we have to ensure, in order to avoid real limitations, we have to ensure that our concentration of sample solution is less than 0.01, and we prepare the sample solution such that concentration of other species, particularly electrolytes, is also low in the sample solution. Then real limitations or deviations can be kept to a minimum, and we can avoid any errors in our analysis. Next, we'll consider the instrumental deviations. Instrumental deviation could arise because of any of these. I told you earlier, due to presence of stray radiation or if polychromatic radiation is used. The other two are also related. So stray radiation, what is stray radiation? It is a radiation that that gets reflected or from the surfaces of, say, lenses, prisms, windows, or any component that is supposed to be transparent in your instrument. So if the radiation strikes, say, a window, it is supposed to get transmitted without any loss. But if there is any imperfection on the window, say like a scratch, then radiation may get reflected. And this could constitutes the stray radiation, because this stray radiation may or may not pass through the sample. It may undergo reflection multiple times because it may hit some other surface, then again get reflected, hit some other surface, and finally reach the detector without even passing through your sample. So presence of stray radiation have to be minimized. How can you minimize this? By ensuring that all transparent components are transparent. There are no imperfections. Most of the components will be inside the instrument so they don't give problems, except the sample cell or the cuvette. The cuvettes are the ones which is handled by the analyst. So you have to ensure that the cuvette is properly maintained. And that's why whenever we take readings, we ensure there is no liquid on the outer side surface of the cuvette. And we also ensure there are no dust particles sticking, there are no scratches on the cuvette, and there are no fingerprints. So you should not touch the cuvette where the measurement is going to take place. You always handle the cuvette from the top by holding it at the top. And how do you ensure that there is no imperfections on the cuvette? You always wipe it clean with a fine tissue paper. This you have to do before placing it in. So and after wiping, do not touch the cuvette in the lower section. So you have to hold the cuvette on the top, wipe the cuvette, and then place it in. This also you'll be instructed well in your practicals. The second one, what I have listed here is improper slit width. Slit width, suppose improper means it could be larger slit width or a narrower slit width. Suppose you have narrow slit width, then the intensity of radiation coming through and falling on your sample would be very low, and maybe everything will get absorbed. You don't get any transmitted light, because what an instrument measures is always the intensity of transmitted light, and then it calculates based on the incident light intensity, it calculates what has been absorbed. So if there's no transmitted light, then it is not able to calculate it. Then if there is fluctuations in single beam instruments, single beam instruments are one type of instruments. If there is any fluctuations in the electrical supply to a single beam instrument, then also it will result in an instrumental deviation. And lastly, monochromatic light is not used, because as you have seen in Beer's law, it starts with when monochromatic light passes through a homogeneous medium. Okay, so monochromatic light should be used. If we are using polychromatic light, what is polychromatic light? A beam with several wavelengths in it. So whatever lamp, any of the lamps that we use in spectroscopic instruments, all these lamps are polychromatic sources. To get monochromatic, which are the monochromatic sources? Pure monochromatic sources are lasers. And lasers are not practical to use with our spectroscopic instruments, because one laser will give light of only one wavelength. So you can analyze only one compound or a few compounds at that wavelength. If you want to change the wavelength, you will have to change the laser source. So how many sources can be supplied with an instrument? As such, lasers are very expensive. And how many, for each wavelength, can a laser be supplied? What would be the cost of the entire instrument? It is not practically possible. And that's why polychromatic sources, which cover a given region of the electromagnetic spectrum, say if it's a visible instrument, the full visible region, extending from 380 to 780 nanometers. Radiation should be emitted by the source. Or if you have a UV instrument, the full UV region radiation should be emitted. That is, say 180 to 380 nanometer. So one such source for visible, one source for UV is given with the instrument. But whichever source lights up, based on the wavelength selected, it will give you polychromatic radiation. And so along with the source, you will have a wavelength selector which will select a few wavelengths around the desired one. So you get almost monochromatic light, and this is sufficient in most cases. So we say monochromatic light has been used in such cases but this is not a major problem, because even if you don't have perfectly monochromatic light, if your sample is not going to show any drastic changes in absorbance because of the use of polychromatic light, not completely polychromatic, a few wavelengths, then there is no problem. Only if at a wavelength away from your monochromatic light, if say 250 nanometer is your lambda max, you want to use 215 nanometers, but your wavelength selector is allowing 200 to 300 nanometer radiation to pass through. If your sample is not going to get affected by any wavelength from 200 to 300, then there is no problem. It will absorb only 250. If your sample has any other impurity, and that impurity can show a huge absorbance at say 225 nanometer, then there is a problem. So provided nothing in your sample solution shows large absorbance changes because of using other wavelengths, then you can very easily use polychromatic sources. Anyway, general practice is to use a polychromatic source with a wavelength selector to get monochromatic light. This type of monochromatic light is not absolutely monochromatic, but it is close to monochromatic light. And lastly, we come to chemical deviations. Chemical deviations can occur when there is any change in the chemical nature of the substance under investigation. This could be due to association, dissociation, it could be due to reaction with a solvent, any such changes which will change the chemical nature of your substance. I've given a very classic example here, potassium dichromate. You all know the color of potassium dichromate, it's orange in color. So when you make a solution, you'll get an orange color. But you would also probably have observed earlier, whenever you've done some chemistry practicals with dichromate, if you take a dilute solution of potassium dichromate, it looks yellow. So when you dilute dichromate, it looks yellow. So there is two different colors. Why does it become yellow? That's because on dilution, dichromate with water undergoes a chemical reaction giving you chromate and releasing H+. Chromate color is yellow, dichromate color is orange. So there is a chemical change in your substance. You started with potassium dichromate, now what you have in solution is potassium chromate. So that's why there is a difference in color. Now, if you use the wavelength of dichromate, say now some of your solution, higher concentration solutions are orange, lower concentrations are yellow, then you will never get a straight line Beer's plot. You will get a deviation. So you have to ensure that all your solutions have the same color. Either you have the yellow solution or you have the orange solution. How can you do this? You can, suppose you want to keep everything in the chromate form, that is yellow solution, then you have to add hydroxide ions. If you add hydroxide ion to the dichromate solution, it will remove these hydrogen ions by reacting with it and forming water, that is H2O, which remains undissociated since water is a weak electrolyte. So in other words, by adding hydroxide, the equilibrium of this reaction shifts to the left. And therefore, your full sample will be present only in chromate form and the solution will be yellow, whatever the concentration of the solution. Even at high concentrations, it will be yellow. If you want to maintain the orange color, then you will have to add acid. Instead of hydroxide, you will have to add an acidic solution, something like HCl, which increases H plus ions in solution. So when you have some yellow solution, if you have added H plus ions, then the equilibrium will shift to the right. And therefore, whatever chromate has been formed gets converted back to dichromate and your solution turns orange. So all the standards ideally should have the same color, yellow or orange. And you can do that by either adding hydroxide to get the yellow color or by adding HCl to get the orange color. And then we can avoid these chemical deviations. You will, if you have all of the same color, but of course the intensity of color will be different. Lower concentration will have light orange, then still higher, slightly darker orange, and so on. But all will be orange, or all will be yellow, but different shades of yellow. Okay, light, dark, and so on. As the concentration increases, the darker will be the color. This can avoid chemical deviations. Now, if you have all solutions orange only, you will choose the lambda max of orange color and go ahead with your experiment. If you have all solutions of yellow color, you will choose the lambda max of yellow color and go ahead with measuring absorbance of all your standard solutions. But if you have both, some are yellow, some are orange, you will not be able to choose any one wavelength. If you choose yellow, yellow solutions will give straight line, orange will give a curve. If you choose orange lambda max, yellow will give a curve and then it becomes straight line. So you don't get a proper Beer's plot. And that is why it is better to ensure that all your standards are either yellow or orange. I hope that is clear. So we'll stop the class here and continue next class.
This conference will now be recorded.
Do you have any doubts with regard to today's class? Anything that is not clear, because these are all very important portions for you from your exam point of view, to understand spectroscopy from your practicals point of view also, because you will be working in practicals based on all what I have been telling you today. So any doubts regarding this? Yes? Not getting any response.